All right. Alrighty. We'll wait a minute or so, see if anybody else is going to show up. But if not, I'm going to start. If you guys haven't yet, I actually listened to this. This is what I chose this topic on. So if you guys actually want to see something, this is what I chose this topic on, and this topic on, and this topic. So all these topics are the top 4 most, I guess, requested topics to talk about for an Monday. So yeah, I encourage you guys to go on and answer it. All the links are on the YouTube or in the description for everything I use. The Colab and the presentation. How's it going? And yeah, I think we're just about gonna get it started. All right. So today is going to be a topic. The topic is Python, Pandas, and Scikit-learn. Pandas and Scikit-learn are 2 very, very popular libraries for Python. So I figured it was only apt that we actually use them in this lecture today. So yeah, I want to talk about this. So first we're going to talk about Python basics, things like variables, lists, operators, things in Python that are weird to Python. Then we're going to talk about Pandas basics, what Pandas actually is, and what kind of tools it sort of offers you. Then we're going to talk about the data set we're going to use today. Today we're going to be classifying a wine quality data set, where based off of the tests that they use to determine whether or not a liquid is actually drinkable, we're going to determine the actual quality of the wine instead. And lastly, there's the SciPy basics, which we're going to be using to sort of figure out or to classify and regress this wine quality data set. Okay, so again, I'm going to say this again, sorry, it's the last time. Today's lecture is going to be very fast, so if you have any questions, I'm going to be here afterwards. And I have a lot of stuff to go to. I'm trying to fit all this stuff into an hour when it should probably be 2. So first, let's talk about Python basics. So let's go straight to code. So I put together this Colab. So in Python, to assign a variable, you don't have to say what type of variable it is before. It's implicit. It means that if we wanted to define A, we just say A equals 5. If we want to define B, we say B equals 5.5. And then C, D, etc. C is a string, and D is Boolean. String is just a list of characters in Python. And D, Boolean, is just true or false. It could also be 0 or 1. So these data types, when you print out A, B, C, and D, they come out like this. So int is just a whole number, float is a decimal, string is a list of characters or string, and a Boolean is true or false. Then we have the operators. Operators are the assignment operators. So here, A equals 10, that's the assignment operator. And then we have A equals 10, B equals 5. We print out A plus B, does exactly what you expect it to do. A minus B does exactly what you expect it to do. A times B, same. All these operators do exactly what you kind of expect. Comparison operators, we have A equals 10. We can see that A is greater than B is true, because 10 is A, B is 5. Print A is less than B, that's false. That's false because A is B. A is 10, B is 5, so that's false. We print A equals B, so this is going to determine whether or not A is equal to B. This basically is an operator that changes your value from 2 sort of numbers of the same type and converts it into a Boolean. So like that's what a comparison operator is. And not equals or not equals is just a sort of exclamation point equal sign. Again, if you're bored, I'm sorry. This is for people this is an introduction to Python. It's going to get ramped up real quick. All right, so first we have the logical operators, A and B. You can see A and B. We have A or B. Instead of using in most languages A ampersand ampersand, in Python we just type out and that's also means you can't have a variable called and or a variable called or, FYI. And not A. We don't use an exclamation point, we use not. That also means you can't have a variable called not. Sorry. If else statements, so if statement x equals 5, if x is greater than 5, then we're going to print out x is greater than 5. So if there's a Boolean value after this f that is equal to true, then all the code in here is run if that's true. Else, if anything above this, if all the things above this are false, then we print the else statement. There's also in Python, there's if elif statement. So in things like Java, you type out else if. In Python, it's elif, which is a little weird, but just something to point out. And here we go. So we can see here that so for this here, what is this going to print out? Anybody? The first one. What's that going to print out?
X is greater than 5.
All right, nice. How about this one?
X is equal to 5.
Nice. Let's go. Let's go. All right. So now lists. So lists in Python are just lists of values that are like things like strings, numbers, booleans. Here, it's going. And here to access these of values in the list, we just supply the list and then square brackets and then the number inside of it. It's always an integer for a list. It has to be a whole number inside of a list. And so as you can see, the output of this would be apple, the output of this would be banana, the output of this would be cherry, because lists start at 0. We're not MATLAB, we're not maniacs. And the negative indexing just takes, it's like the opposite. If you were to start at 0 here, then -1 would be here, -2 would be here, -3 would be here. That's something awesome about Python. That's not even weird. We hope all languages do that, but they don't. And the length of the list, instead of doing the list.length, you use this function called lane that you input the list into. And something to note, if there's anything that is accessible via these square brackets, it'll count all the possible values inside the square brackets. So length can count anything. Okay, so slicing. Slicing I love in Python. This makes Python Python, to be honest. Because the slicing means that you can say, I want a portion of the array from the start to the end. And the start value is inclusive, the end value is exclusive. And so basically, if I say I only want fruit, so actually let me go up here. Let me take fruits, put this down here. So if I say I only want the first two of these things, apple and banana, apple and banana, we only want 0 to 2. I can just say, oh, I want the indexes from 0 to 2, and we take out that 2 because it's exclusive. And also regarding that, if we put a colon before and then we put the 2 here, it just takes everything before, so we don't even have to say 0 to 2. It just knows that whatever's before the colon, it wants all those values. And same thing, 1 colon, we want to start at 1, and we want to go to the end instead. And we want to go to the very end. Okay, so these are 2D arrays. 2D arrays in Python, so these aren't arrays, these are lists. Actually, I'm going to change this. There's a distinction. A list in Python is a native basic array. An array in Python is a NumPy array, which is completely different. Well, it's not completely different, but it's different, and I'll show you guys what NumPy arrays are soon. So accessing 2D list elements, so to get this first element, or 0, 0, so 0, 0, this would return 1. 1, 2 would return 6 here, and then 2, 1 would return 8, because it's going to 2, 1, 2, and then 1 over. So can anybody tell me how I would access 7? Anybody? Anybody got that for me?
2, 0.
Attaboy, Bob. Let's go. All right. So now we can slice these matrices using this. We can just say like matrix. We just want the first one. We can slice the rows. We only want 1 to 3 rows, 1 to 3, or the last 2 rows. Here we can just get the first two rows, which is 0 and 1, because it's 2 is exclusive. We have 1 to the end, which is the last 2 rows again, but instead we don't have to say 3 because that doesn't really matter. So slicing columns, I mean, it's pretty easy. We just, so for row in matrix, and I'll talk about loops down here. We basically just put single line for loops in and create a new list. So basically we're talking about that right there, for row in matrix. We're basically taking each row in this matrix that we made up here, and we're taking that value, right? So then we go for, all the way down here. So for row 0, or we're taking like that first value in that row, and we're outputting it into a new list. Does that make sense? Okay, cool. Call 0. So you can do the same thing with row 2. That's just an example. And then you can do a subset. So you can do slices in this. So we go to the list and we go to each list. So for example, the first one, 2, 3. We want the columns 1 to 3 for that row here. So we just get here 2, 3, 5, 6. Let's go back. Yeah, here 2, 3, 5, 6, 1, 9. That makes sense to everybody. Awesome. Okay. So loops are pretty self-explanatory. So basically, I have this I that I want to keep adding 1 to, while I is less than 5. We print I and then we increase by 1. Can anybody tell me what the last number of this is? So like when I run this, what's the last number that comes out? 4? Okay. All right. Run it. Nice. Let's go. All right. So then we have apple, cherry, and banana. So this is a for loop. In for loops in Python, we can just put for, and then we define a new variable name in the list. So this will just go through the list, or in Python it's called an iterator. So anything that starts at basically 0 and you can sort of iterate through. So now we'll talk about NumPy for a little bit. NumPy basically is like a way to make arrays in Python a lot easier to work with, where, for example, instead of having the 2 square brackets, you can just do the first and then comma the second. When it's a NumPy array, you can do 1, 2. So basically the same, but instead of having to do those square brackets, you do like that. So it's just comma instead. What this allows us to do is then if we have 2D arrays, we can then slice the 2D arrays instead of having that weird for loop thingamabob. So now we have 0 and comma colon, for example, instead of having that for in whatever. And so basically all these here are just the sort of equivalents as the last one, but in NumPy. So as you can see, it looks a lot cleaner. Slicing columns, same deal. But instead of, so this is like row, column in NumPy. I should have said that earlier, that's my bad. And then, slicing a rectangular, a subset, you can just put 2 slices in and you can slice that. That's that, whatever subset of the array you want. Okay, so NumPy has a bunch of convenient stuff, so you can do like numpy.0 and it creates a 3x4 matrix. Then numpy.1s just creates a 2x5 matrix that's just a bunch of 1s. This one's just a bunch of 0s. Sorry, I forgot to mention that. It's a 3x4 matrix, so just a bunch of 0s. So if I print these out, you can see this first one's a 3x4 matrix, so it's 3 rows, 4 columns. Matrix of 0s, 1s. This one here, let me go here. This one just makes a random matrix of anything, 4x3 matrix of random numbers between 0 and 1. NumPy also allows you to do reshape. So if you get an array that's 1D large, then you can reshape it into 2x3. So for example, when you multiply the rows by the columns, it has to equal the length of the array you're going into, or else it'll give you an error. Again, we have transposing a 2D array. So does anybody not know what a transpose is? You don't know what a transpose is? It's basically switching the rows and columns. yeah, so like you can just basically like whatever used to be a row column, it just switches them. So it makes it, so I mean, instead of doing this in Python, which is, it would be a lot harder, you just put .t and it works. We're not actually going to go over what a dot product is, but if you have taken linear algebra, things like dot products, things like cross products, all those are already defined in NumPy if you have a 2D array, so you don't have to do them yourself, which is awesome. Yeah, and then so now let's go back. That was a lot. So let's go back. Now let's go to Pandas basics. So now we kind of understand like Python and types of values we can have, and what NumPy lists and stuff like that are. Let's go and talk about what a data frame is. So typically we import pandas as PD. If you ever see PD inside of a Python file, it's probably pandas. I don't know if somebody's not importing pandas as PD, they're actually a maniac. You should probably send them to a mental hospital. It's almost always PD. But yeah, so basically if we take some 2D array and we give it, again, instead of this, we give it columns, we can create a data frame from that 2D array and define the columns, and it outputs something like this. Okay, where we can access these columns, and we know like each row is sort of given an index. Does that talk about that here? No, it doesn't. So then each row is given an index, and we have our columns. So we're going to talk about that later, why we want that. So this kind of looks like an Excel sheet, right? Instead of like a 2D array, something that you're more familiar with, a little bit more abstract. And so basically now it creates this new index column, and it creates a column like the new columns, and you can access these columns as you want. So yeah, creates a new index column, yada yada. And then creates a calls column. There we go. So yeah, this 1D array columns, that's just added at the beginning. So when you go to add an Excel sheet, typically the first row is automatically made into the column row. So if you have data that doesn't have labeled columns, you have to specify what the columns are. Pandas versus SQL. Does anybody here know SQL? Or should I do this? No? Alright, well, when you go to access a Pandas data frame, just one column, it's a series. So you should think of a data frame as a list of series, for example. So a series is just like one column of a data frame, and a series is also indexed with that same number. So all the series that you have the same index, and that's why it's able to make a data frame. Okay, but if you access multiple columns, it doesn't return series, it returns a data frame, because it's a Pandas list of series is a data frame. So there's that. Yeah, so as you can see, when I take out this series, this index stays the same no matter what. Okay, so that sort of, yeah, so this kind of acts like as a select from df. You want all the, like, call 1 and call 2, call 3, etc. Yeah.
Which of those pictures is SQL?
This one is SQL. I'm trying to compare like this. So like this select is just like if you were to write it in SQL, this is what it would be comparatively to. So a series, data frame, yada yada, dictionary of series. I guess yeah, it's a dictionary because instead of a list, so it's more like a, because an index doesn't have to be a number, it can be a string or a. And I think I talk about that. I think I talk about that eventually. Yada yada. I keep going over this again and again and again. Yes, the default indexing is just the range between 0 and the end of the column, but there you can also make a different index. Hold on. So if you want to specify what your index is, so if you have like dates or something for like stock values or whatever, you can actually specify the index by just saying, when you say it, you just say index is equal to that list that you want the range, that you want the index to be. So that could be super useful if you want things like to access them from the date itself. Indexes must be comparable. That means it must be able to know when it sees it, which one's higher, which one's lower. Does that make sense? Yeah. Higher, lower, equal to. And indexes are always unique. Each index thing is unique, and they are kept in order at all times. So whenever you go to access something via the index, it knows exactly where it is, and it can access it super fast. Okay, more resources. If you wanted to learn more about Pandas, here's a link to everything. It compares it to other tools. If you guys are used to other tools, I think that's super useful because like whatever you know is relative. So if you have a tool that you currently like, then you can compare it to a new tool in some way. And yeah, so you can open up, CSV files, which just stands for comma separated values, where commas are the delimiter, what makes a new column, and a new line is just a new line character, a \n in Java. And yeah, custom columns, everything. So let's get to the fun stuff. So the wine quality data set. So the data set I chose to use today is from University of California Irvine Machine Learning Institute. It's basically just like a test data set that I found that they did a bunch of research and they compared models on just to compare like the actual sort of how effective a model is. But I use it because I think wine is cool. And then it's basically, I found it from Kaggle originally. And Kaggle typically has everything you need to know about the data set. But what we basically want to know is that the content for this is that it has like the fixed acidity, the volatile acidity, the citric acid, like all these numerical values in order to they're typically used to determine whether or not a liquid is consumable. But instead, for example, if your boss goes, can't we use these values to determine how good our wine actually is? Then, then this is what you have to do. This is what so basically, you get all these values, and then you go back here. So the input variables here are based off of these psychochemical tests, which are often used to test, I just said that. You have these input values that are all continuous values, and then you have this target variable, which is a quality. So quality is just a value between 3 to 8 that determines how I guess, quality the wine is. Very subjective. It's going to be kind of hard to predict, but I mean, our boss is our boss, right? So here's some SciPy basics. So let's go. Can I go here? So Scikit or SciPy or Scikit-learn, whatever you want to call it. I guess SciPy is Scikit-learn is just a library of tools of machine learning tools that are just available to you, so you don't have to code it yourself because that would suck. So some of this stuff is terrible. But basically, what we're going to be focused on today are the classification and the regression portions of this actual library. There are a bunch of portions to this library, and I very much encourage you guys to go in and just look at some of the examples because they're fucking awesome. But yeah, I love this library. So all right, let's go back. So mean squared error or linear regression. Let's talk about this. So mean squared error sounds threatening, but it really is not. All you're doing is basically when you do a linear regression, what you're essentially doing is you're fitting a line that minimizes the mean squared error or any error, however you define the error to be. So what you're doing here is we're basically quantifying how far our prediction is. So if green is the actual, what the actual data point is, and blue is the prediction that we generated, for example, the red line is the difference between those two, or the error. Does that make sense? This is important. Sweet, okay. So now we just take one of these points. So for one of these points, we take the error, and the error is equal to the absolute value of the actual minus the prediction. So that's pretty self-explanatory. It's pretty easy to figure out. And to instead we do the mean squared error because it makes it so it doesn't make positive and negative values, because if you multiply negative by a negative, it's positive, and a positive and positive is positive. And it also allows us to sort of weight values that are further away higher. So if it's really far away, then it's going to have like a different type of value. Okay. So now that we have that, let's go back and code this in Scikit. So I go here. Okay. Here we go. So, I should probably. I've screwed this up. It's okay. We're gonna go over pandas in code now. Okay. So now, say we have this age, name, age, and gender here. We basically can create this data frame from this data that we have. So this data is a dictionary, like a key value pair. I didn't talk about this before because I'm going to talk about it now. Key value pairs are basically just like you have a key, and then when you go to access it, instead of putting in a number there, you just put the key to that value. It's basically that. So basically, when we input that key value pair, we're able to get this row and column. So this is just another way to make a data set. Note that the number of values in the dictionary is very important, and where those numbers are is also very important. So if you're looking to make it this way, just make sure that you keep that into consideration. But basically, we call a type on this df, and it returns this pd.core.frame.dataframe. All we need to know is that last part, data frame. So accessing elements in the data frame. So basically, if we just want to get the name column of this data frame, or like this part here, we can just say df name. That's pretty easy. And this returns a series, as we kind of talked about before. And to get multiple columns, we just input a list of columns. Pretty straightforward, pretty simple. And the type of this, we talked about that again, is a data frame, because it's multiple series. To get rows, it's a little more complicated. We just do df.locate for loc. Loc just locates the row. There's also iloc, which locates the instead of like the actual value of the index, it locates the where it is in the frame. So you have like say an index of strings and do iloc 0, and it just gets the first one that's available in the data frame. Okay, this returns a series. df.loc 1, 3. Can anybody predict? Oh yeah, and this is a type series. Instead of it being indexed by 0, 1, 2, it's indexed by those strings. Can anybody tell me what they think df.loc 1, 3, what type that's going to return?
A data frame?
Yeah, data frame. Let's go. Yes, sir. It's a data frame. Awesome. So yeah, so you can basically go in here, and then same thing with NumPy. You can go in here, you can get the df.loc, and then the row value, and then comma column, like the comma string, like the column string. So you just basically get like the first element of this array, which up here, you go up here, is Alice, or hold on, is Alice right here. Oh my god. Yeah. So that's pretty simple. So like this is how you access actual values, like specific values in the array. So yeah. To add a new column, you just say df profession, one that's ever been called for. If you do this, it'll overwrite the last column if it's the same as a column before. And then you just set what you want that array to be. Again, where it is in the list is very important. And note that the lengths, whenever you do this, should probably match. If they don't, you'll have a bunch of nulls in there, and it'll just be weird. Yeah, so then now we have this new data frame that has this profession column with the list we just added. Yeah. All right. So to filter data frames, this is cool. We can filter data frames. So df filter is equal to df, and then we call this df age is greater than 30. It's kind of weird, right? Why do we have to redo df? Huh? well, give you a little knowledge bomb. If we go like here, this just returns a series of true and false values. So basically, if we wanted to, we could just send in a series of true and false values, and it'll return a new data, and it'll return the data frame. So if we go like this here, like that, it only returns the ones whose age are greater than 30. So you can see like Charlie and David are the only ones that are greater than 30. So that's a pretty cool little tool if you want to filter out some data. Now sorting by column values. So basically you can just do this df.sort values, and you can say what you want it by. So let's say we wanted it by age, and then we could say whether or not we want it ascending or descending. So it's kind of like in Excel when you have like the little column thing, and you just have like you want to sort by that column. This is basically just doing that. It's just redoing it. So now we sort by age, and then since it's not ascending, it has to be descending, which means that it descends down the age, so it like resets it. Okay. So this is a little off topic, but I thought it was something important to talk about. You can also merge data frames. So if I create two data frames, left and right, and one has age and one has salary, we can merge them using these methods: inner, outer, left, and right. So inner just takes the inner portion of this a data frame, sort of
The intersection.
Yeah, the intersection. The outer just takes all of everything. The left just takes anything that's in the left one, or the one that you give it to first. And if it's not in the left, then it doesn't add it to the data frame. Right is the right, so it's basically just the opposite of left. So here, if I were to go here and I were to do df merge here, you can see basically that the salary is not a number because Bob, we didn't define a salary, and then name is Charlie, and age is not a number or null because we didn't define what his age was. So can anybody tell me what they think left will return? So if I go back up here and I show you guys, so if I go right here, so let me actually just hold on. Here. Okay, so can anybody tell me what they think this left is going to look like?
0, Alice, 25, 50,000, have name, age, and salary for Alice, and I'll have Bob, just name, age, and a number for salary.
Yeah, perfect, because age doesn't have because Charlie doesn't have an age. Perfect. There we go. Awesome. So it's just a cool little thing. Instead of using SQL, you can just use Pandas because Pandas is better anyways. But yeah, so basically I found this data set. All this does is just download the data set to a CSV file locally. That's all it does. It just makes this file right here, wine quality red CSV. And to get CSV files, we talked about this, pd.read CSV. We get wine quality red. And then in this file, some guy was being super extra and made the delimiter a semicolon instead of a comma. I don't know why, but we just defined what the delimiter was to be a semicolon. That's how it is. So basically, this is what the data set looks like, and now we have all these columns of fixed acidity, volatile acidity, citric acid, residual. Doesn't really matter, does it? And except for this one where we have quality, that's just 3 to 8. It's supposed to be 0 through 10, but I guess the person that was doing this didn't like wine very much, didn't put any 10s, so I guess that's how it is. Yeah, so yes.
What's a delimiter?
A delimiter, so a delimiter is basically something that separates or like it limits something. So when you're going through a CSV, basically it looks through each line and then it looks for the delimiter. If it's a delimiter, then it starts the new column.
Okay.
And then basically boom, 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 and then when it hits the new line, then it creates a new row.
Okay.
Yep.
Thank you.
No problem. So data.info. Data.info. So as you can see, all these are float values except for our little quality value, little target right here. Basically, we have these 10, 11 columns. This starts at 0. I can't do math. And they're all floats, so they're all continuous values. If we look into this, we can describe. So this describe is just, it's supposed to look like this, but I think that's weird looking. So I just put .t again, and it goes like this. So now we have the count, mean, standard deviation for all these columns. So as you can see, the min and the max of this quality value is 3 and 8, and it doesn't deviate very much. So it doesn't have a very high standard deviation. So one standard deviation is essentially like, I'm not a stats major. All I know is it doesn't deviate very much. So I don't know how to need to explain that. Yeah, what's up?
Did transcribe flip the columns and rows?
Yeah, so .t is just transcribed. You just change the rows to columns and columns to rows.
Right.
So like the indexes of the two.
Mm-hmm.
Okay, so here's, I know this is a lot, but if you look at it, it's not that hard to figure out. So this is something that I like to look at the data to see how, I guess, variable it is. It's called a pair plot. So a pair plot is essentially just like, it takes all your columns inside of your data frame, and it plots out the scatter plot. And in the thing where it would be itself, it has the kernel density estimate, which is essentially just like what the density of that value at like where it's at currently. So it's almost like a distribution. The area under this curve is 1 if it were to be like weighted correctly. But yeah, you can see how this is going to be kind of hard to predict, since like if we set the quality to hue, you can see like the different colors of the different qualities. So like it's not very like correlated, which is not very good for a lot of reasons. But our boss is telling us we need to figure out how to make the best wine in the world, and this is how we do it. Oh shoot, I don't want to do that. Okay, so that takes a while to run. So we're just gonna skip over that. Didn't mean to do shift tab there. Is this gonna go? Oh my gosh. Start runtime. Okay, it's good now. I think. So now we basically make this target the quality, and then we just drop quality and make that our features. So drop basically is just a function for data frames, where we take the data frame and then we just drop that column. We don't need that column anymore because we just made it into our target. So then we do train test split. So this basically just takes our data set, takes a value between like 0 and 1, and if it's greater than, let me go over here. If it's greater than 0.2, then it puts it into the training set. So there's two sets. There's a training set and a test set. The training set is just like what you're going to train your data on, and the test set is what you're going to test your data on, which is like how we're going to sort of figure out that our model is actually working, because it's going to be data that it's never seen before. So it's basically like testing our model to see whether or not it's going to work on data that it's never seen before, which is a pretty interesting concept. So yeah, then we basically have this test size, and we set a random state, 42, test set, train test. So then this outputs are the input values for our train, the input values for our test, and then the target for our train and the target for our test. So basically it just basically takes like, if you were to have like an Excel sheet, it's just like taking like 80% of it, putting it into a new Excel sheet, and taking the other 20% and putting it into another Excel sheet, just so we can just like kind of like work with it. So yeah, we run this linear regression. So I'm going to go back. I'm going to be talking about linear regression here. Where is this? Oh yeah, I talked about linear regression. I'm going to go over it again. Sorry if that's boring. Basically, we're just minimizing the error. We're doing the actual minus the predicted to find the error. This is just like a visualization that I wrote out before presentation today, just because it's pretty important. And yeah, that's pretty much it. You can see like the red lines, the error is the difference. We do squared because it penalizes values that are further away a lot more. Yeah, linear regression is just minimizing error. Boom, boom, boom. Scaling inputs. So, sklearn at pre-processing. This is insane. So there's this thing in sklearn called standard scaler, which basically fits your data towards a normal distribution, or a normal distribution being like it has a mean and a standard deviation, like a location and a scale for this standard deviation. So, for example, like here, let's go back to this. Oh, I don't have the pair plot anymore. I played myself. All right, we're gonna go back and get this later. So we have this standard scaler that has a mean and standard deviation. So basically, like a location and a shape. So there's like a scale, like. So for some distributions, the standard deviation would also be like the shape of the distribution, but standard uses Gaussian. There's also something called a min-max scaler, which just takes all your data, gets the min and the max, and then just creates a linear line between the two, and then just basically says where it falls on that line between 0 and 1. So that's just a min-max scaler. -1 and 1, my bad. Yeah. There are a bunch of other methods. So let's look at this Desmos real quick of what like a standard scaler would kind of look like. So if that mean is that blue line, you can see as we change the mean, it just moves around this distribution here, right? If we change the standard deviation, so if we increase the standard deviation, is it going to get like wider, or is it going to get like closer? Can anybody tell me? Here. Oh, shoot. Let me just.
It's gonna get wider.
Yeah, if we increase the standard deviation, it's going to get wider, yeah. So it's going to go like that. So if you want to go around and play with it, this link's on the slides. This is Desmos. If you guys don't use Desmos, I would suggest it. It's my favorite. It's one of my favorite tools, just to like go around and play with stuff. But yeah, there's a bunch of different types of scalars. The one we're doing now is we're basically scaling a value between 0 and 1, just based off of like the, I guess, where it falls in this distribution. So that's essentially what we're doing. So let's go back. Oh yeah, and then we have pipelines. 2, 3, 4. Oh, it's 4 now. Okay. Oh yeah. So for example, like this, for this one here, the mean of this would be this value, and then you can see that it's like it's very like it doesn't have a lot of variance. If anybody tells you variance, it's just the variance is just like the square root of the standard deviation, or is it squared? It's one of the two. It's square. It's a square. Yeah. So they're basically the same thing. Just they're basically the same thing. When they say variance, they also mean standard deviation. We talked about train test split, linear regression. Oh yeah, we're here now. Mean squared error. Yeah, and then this is just this just gets the mean squared error from that value. So we input into mean squared error the target test and the target predictions, and it outputs this mean squared error that we want here. And that's just so basically the interpretation of this is that it's it's the square root of this. Let me see if I can take square root of this. Hold on. Oh no. It just means that the average that it's off on is equal to is less than like 0.62, for example, like the average that it's not hitting the right thing. That's like the interpretation of it. So then we introduce these things called pipelines. So pipelines essentially lets you create this like the scalar and put everything in like one linear thing. So you can scale your sort of input values and then regress, and then that regression then outputs what your target's supposed to be. So then this pipeline, essentially you can just call that same thing .fit. Oh wait, yeah, .fit, where you put in that input train and then you put in the target. So like this is what we're training it on, so it knows what to expect. It can chain, it can solve for the optimal line of best fit for each feature for that target value. So then we do LR prediction is equal to pipeline. So then we just predict on the on those input test values. So that will output again what it thinks the predictions are. So like it basically just take. Let's go back to what I drew before. Hold on. So basically, it's just taking this line. It's just saying one of these inputs fitting at that line, and then saying what its prediction are, what its prediction is. Does that make sense? Sweet. All right. We're cooking with gas. All right. I didn't think I was going to get through all this, by the way. All right. So now we have this pipeline linear regression, and now we can basically just go all the way through. I get this mean squared error, and then the score is not mean squared error. I honestly don't know what this is, but it's pretty close to the mean squared error. I'm pretty sure it's like maybe something a little bit different. They might be adding, I don't know, some extra values. But it's essentially the same thing. It's just what it uses as the loss in this function. So basically, this is me showing the results. So this might be a little bit confusing because there's these orange ones, but I put 7 bars for what the test values actually are. So this is like the target value, and then these are the counts of those target values. So we predicted between here a lot. So as you can see, like it could be like here or there a lot. So it's essentially just saying like these are our predictions. So like as you can see, our predictions very much likes to fit towards like a normal distribution because that's what we trained it on. But the values go a lot further away, so that means like the outliers aren't very good in this case. Well, we aren't very good at predicting outliers. But basically, since essentially the output of this is categorical, so it's like an integer. It's either 3, 4, 5, 6, 7, or 8, and we output like a number between like 3 and 8. It doesn't really like. It's kind of hard to linearly regress this. So basically, let's go back here. Label encoder. Yeah, label encoding. So we do something instead called label encoding. Label encoding is pretty cool. So basically, we take, so if we have a column, like, for example, if it's not like 3, 4, 5, 6, 7, 8, and instead we have like a column of countries, essentially takes this column of countries, creates the number of like a bunch of new columns, essentially, and it just takes these new columns. So like India would be 1, 0, 0, 0, for example. So like that's because it is India, and then it fills out the rest of them as 0. So then we can instead just try and predict each column. Does that make sense? And then get like a confidence for each column. Choose the one that has the greatest value. Okay, like the output. So then, instead of fitting a linear model, we can do something called a logistic regression, which is basically just taking this linear thing, putting it into something that's a little bit more usable, and makes it into something that scales the value between 0 and 1. So we basically take this, the output of this linear model. So we still are fitting a linear equation, but instead of fitting the linear equation, we're essentially just, putting that linear equation into this. That's basically it. Any questions? No? All right, sweet. Then we have logistic regression. So basically, then what we do is we generate this boundary, and if it falls on this side of the boundary, then we're going to say that it's true or false. And how far away it is from that boundary, or like how far away it is, determines its sort of like confidence in a way. So if it's really far away, then it's going to have a really high confidence. If it's really, my bad. This is the confidence. The y is the confidence. That's my bad. The y is the confidence, and how far away, and whichever line this falls on, instead of it being like the actual value, would be, what the actual value is. So say you put in x, and you put in this. So say x is here, for example, and y is, hold on, my bad. Okay, so let's put it this way. If x and y are 2 independent variables, right, so we have 2 two inputs where y is just the, like, you know, the actual value that we're trying to predict. So y would be like one of those columns that we generated in the label encoder, for example. So if x is one of the inputs, it would basically draw a line up to x, put where that value is, and then that would be the confidence. Okay. Did not confuse anybody. I'm sorry if I did. Okay. Yeah.
What does it mean by true and false samples?
What does it mean by true and false samples?
Yeah.
So it basically tries to fit this line. So true samples are like the actual, like what, like these are like our targets. So we're basically putting the targets on a graph y to x. So x being one of the input values, and we're fitting this equation to have the maximum number of values on this side of the boundary that are true and false on the other side of the boundary. So we're basically trying to fit this line so we have like the least amount of, I guess, so we have the most amount of true answers that are like, if an answer is 0, then it's on this side. If an answer is 1, it's on this side. Okay? Yeah.
Would the reason like why it's shaped like that be in the sense that when the lower y is, the lower the confidence of the algorithm, it won't be able to say, okay, like this is true as much as it's false.
Yeah.
And then, so for example, if y is 0.99, so it's 99% confident, that's why there's more true values.
Yeah.
It's able to.
It's basically trying to make this line as vertical as possible, so it has as much of a boundary as possible. Because then, yeah, because you're right. Because then it basically has like a, because this where you put this boundary is what you're trying to solve for. Yeah.
What I don't know if this makes sense, but is like that y-axis the estimate and x-axis the actual value,
Yeah.
or other way around?
Yeah. So y would be like you're trying to predict like the class. So each class would have its own, and then you have like 10 x's. So it's like 10-dimensional. You're fitting a 10-dimensional a logistic thing. But as you can see, when you're looking at it in code, it doesn't look like that. It just looks like you're running a logistic regression on the data. But the actual meaning of this is like you're trying to fit this boundary to fit like. So this y would be like the output of the confidence. And then, so basically, now we're setting this boundary for each input x, and we're basically saying if this boundary is less than the sample, then it's y, and then we just we just get the value that has the greatest y for each of these inputs, and we say like that's the class. It gets very complicated. I don't know why I chose to go into this, but basically, just know a logistic regression is not a regression; it's a classification. That's the only thing. It's regressing a boundary, and yeah, as you can see, it doesn't really converge because our data is not very good, and our accuracy score is not very good. But that's kind of misleading because our accuracy, because we have like 5 classes, and so like if it's like, say it's a lot harder to guess the correct class when there's 5 classes versus if there's 2 classes, because like the odds you get the right class are a lot worse. So if like for example, if you were to randomly select a class, it would be 0.2. So it's a lot better than randomly selecting what the quality is. So yeah, and then so the actual score that it has is the accuracy. I don't know why the mean squared error is not the same as the score before. I'll look into that. I didn't have time, but yeah. So then we can visualize these results, and since we're visualizing just the class, we can see that like a lot of the stuff that I guess from 5 and 6, it kind of sort of fits the distribution that of the actual test labels. Okay. 3. Oh no. Let's go back to 4. Wait, 1. Here? Yeah, I'm here. Okay, so let's go down. So we can basically display this thing called a confusion matrix, which this actually helps a lot for visualizing it. So if this is the label that was true, this is the predicted label. That like this is the value that the model predicted, and this is the true label. So we want all of our values to fit on this portion right here, right there. Okay, so the fact that we have a lot of our values like very close to what it actually should be is actually a pretty good indication of like one quality. And so like this shows that it's not as bad as it looks. Okay. Yeah. Is there a question? Okay, I thought somebody raised their hand. Okay. So now let's go down. So decision trees. So this is a very high level of decision trees. So instead of doing a logistic regression on one of those things, we go to each column and we figure out where we can draw a line to essentially group the most yeses with the least amount of no's in where we can draw that line, and then we keep doing that until we run out of lines we can make to segregate the data as much as possible. So this is kind of like a visualization of how it works. So yeah, combines numerical. So this can also combine numerical and categorical data, which is crazy because that means like you can have like, instead of just having numerical data as your inputs, you can also have different things like male and female, or like, so it's just a way to segregate the data. Yeah, and the top of the tree is the root. So this root node is like the most important node because it basically is that one line that's like segregates like at the most yes and no's as possible. So like, for example, if you're thinking of this like a doctor, if you do a decision tree on like patients, for example, and like what their symptoms are, and if one symptom is the difference between a flu and COVID, for example, then that one symptom would be the root node. So like that's like, you would know that like that segregates the data as much as possible, but I think it's pretty interesting. And yeah, and then each leaf, so a leaf is produced like when it's at the end of the tree, a leaf is produced when there's no line that can be drawn that segregates the data enough. It's pretty intuitive. So this is actually a pretty explainable model if you need explainability in your model. So this gets us a little bit better score on the data, and its confusion matrix is also a little bit better than the logistic regression. So basically, we go back. A random forest is basically just a bunch of these trees fitted, and then they each get a vote of what class it wants to be, and then the tree with the class with the most votes gets determined to be that class that it's predicting. So, does that make sense, everybody? Okay, sweet. So now we go here. This should get an even better score. Come on, you got this. Yeah. So this gets an even better score, and you can see the confusion matrix output from that one. So we're just getting better and better here at this point. So yeah, we keep going on and on. So basically, now let's talk about support vector machines. How much time do I have left? I have a couple minutes. So support vector machines, and we've gone through a lot of content at this point. Support vector machines basically take, like, say this is your data, like x and y, like x and y being like two, like these being the classes, like blue and red being the classes, x and y being two like inputs, two different types of inputs. You can basically square the like this, like the like square x square y, for example, and then you get this z instead. So we get this x. So this is like x squared z, and then it basically creates a whole new dimension. And then now we can just draw a hyperplane through the data, so it's better able to fit like this. So instead of fitting a circle, for example, we're fitting another line, which is a lot easier to fit in general. So yeah, then let me just show you guys this visualization. This is a really good visualization. So yeah, blue and red dots are not linearly separable. Polynomial kernel, yeah. It's basically, it takes these dots, squares, it's basically x squared plus y squared, creates a whole new dimension z, and then now it's able to basically fit a line or like a linear equation to group the data like that instead of drawing a circle. So then now that data is grouped. All right, come on, you got this, I believe. So now that data is grouped like that instead of like a normal linear equation. So basically the rules in computer science is make everything into a linear equation. It's pretty much the rule of computer science. So yeah, this is the last time we're gonna code. If I've gone pretty quick, but yeah, so we can do a support vector regression, which is basically the same thing. So our results are better. Oh shoot. Yeah, so then now we can just round those values to get the classes, and you can see that we're pretty close on our tests and predictions here. So we can get an accuracy score of 60%, and then this classification. Oh, I guess we're doing worse than a random forest. That's my bad. But yeah, essentially you can just now see we have a confusion matrix for support vector machines. And again, there's so many things that you can do with scikit-learn that this is just like the surface of the iceberg when it comes to scikit. Like there's probably upwards of like thousands of functions that are just like these, that are just research papers that have been implemented and added via open source. And yeah, I think that's pretty much it. So hope you guys enjoyed my presentation. Have a wonderful day. Awesome. Any questions? Now that I'm done? Yes.
Would a professional, like someone who's like their job is machine learning, would they use something like scikit-learn?
At Dun & Bradstreet, they only use scikit-learn.
Oh wow.
Yeah, where I work, they use TensorFlow for some things, but you know, for some some modelers only use scikit-learn because it's a lot more explainable than something like TensorFlow or PyTorch. So like when explainability is really important for something like credit scores, where you have to explain what values are like important for the actual model to predict, scikit-learn is so much better because it has like a lot. I don't know. It has a lot more different. It has a lot more variation of models. For example, like in TensorFlow, if you only do one layer of the network, all they have is a linear regression or like a logistic regression. They don't have like all this extra stuff that scikit-learn has. Yeah. Anyone else? Yes.
Yeah. If we go back to support vector machines.
Yes.
So in our example of one quality, if we like separate one quality from 0 to 10, do we have like 10 different dots? So for now, we only have triangles and circles.
Yeah.
So if we want to classify like quality from 0 to 10, do we have 10 different type of dots and we want to?
Yes, 10 different colors. Yeah.
Okay.
Yeah. So then we're basically separating line color by color by color. But again, each color is going to get its own line instead of it being like, so like when it comes to like a logistic regression, each color gets its own line value where it's between 0 and 1. Does that make sense? Okay. Awesome. Sweet. Yes.
So with normalization, I kind of don't grasp. I don't know if you discussed it, but you did cover normalization just a bit.
Yeah. Well, I had so much to cover. It's okay. No.
Yeah.
I'm just saying.
So like, at what point do you normalize your data? Because I know you, like sometimes you don't want your training data in there. Other times you might have like data that exceeds that normalization that you did on your training data.
Yeah.
How do you, like, at what point in the process do you normalize your data?
So basically what I typically do is so there's an input space, which is like taking your input, cleaning out which columns and stuff you actually want in your model, and then once you have your input space or like the columns and like values you want, then you create a feature space. which is basically creating the features that get inputted into the model instead of the inputs. So like the feature space are all those normalized values. So like when you're saying like at what point do you normalize the values, it's basically like right before you throw it into the model.
Okay, do you normalize the target space as well?
Well, you can if you want, yeah. Typically no. It depends. It depends on what you're trying to do. Like we technically what we did here, that's normalizing. Technically, we're like normalizing into different columns between, and then each column is 0 or 1.
Mm-hmm.
So this is technically a normalization, but it's not like typically what people would think of as a normalization. Okay, awesome. Yeah, all right, I'm gonna end the stream really quick. If you guys have any more questions, let me know. And yeah.